Let me go through a work example on how to select a fan and duct. So in this question, let's say we have an AHU and it passes through duct section A, B, and is split into BC, BE, and BD. And we also have three respective dampers just before the diffuser. And the VAV pressure loss chart is also given over here. So let's do the first part, which is on duct sizing. In order to write down what are all the rectangular duct dimensions, it's good to prepare a table like this, which means we write down the four sections. In this question, there are four sections: section A, B, BC, BE, and BD. So each of the section will carry certain amount of air volume. So BC and BE will be 800 liter per second each. BD is 2000. And finally, AB is the main duct, which is the sum of these three airflow quantity, 800 plus 800 plus 2000, so 3006. And with a friction loss of 1 Pascal per meter, we can plot onto the friction loss chart of these three particular air volume, which is 800, 2000, and 3006. Now, let's plot onto the friction loss chart. The first air volume is 800, so 1900, 800, so 800 is along this vertical line. So the intersection point with 1 Pascal per meter will be over here. The next section is 2000 liter per second, so it will be along this vertical line and it will cut this point over here. And finally 3006. This is 2000, the next vertical line is 3000, and this is 4000. So 3006 will be somewhere in between, maybe over here. With these 3 points plotted, let's read off the round duct diameter first. So for the section that carries 800 liter per second of air, the round duct diameter is just above 400 millimeters. So 405 will be a good estimate. As for the next section, it is between 500 and 630, so it will be around 575 over here. And finally, this is between 630 and 800, so a good estimate will be around 715. So that's the three round duct diameter. And for air velocity, for the smallest duct, the air velocity is above 6 but below 7, so a good estimate will be around 6.3. The second duct, it is below 8 and slightly below 8, so 7.8 will be a good estimate. And finally, the last point is just nice on the 9 meter per second line, so we can write down the velocity as 9 meter per second. So with the values that we have just read off, we can fill in the next two columns, which is the air velocity and round duct diameter. Next, we will use the conversion table to get the respective rectangular duct dimension. So the three round duct diameter that we need to look at is 405, 575, and 715. First, for 405, we will select a duct, maybe this one, okay, at 409. So if you are going to select this particular rectangular duct, it will be 400 times 350. Next is 575. So 573 will be quite an obvious choice. And with that, the rectangular duct dimension will be 550 times 500. And finally, 715, we will take the 711 millimeter round duct diameter over here. So it will be a square duct, 650 times 650. So now we can fill in the next column, which is the rectangular duct dimension. Once you have filled up the rectangular duct dimension, the next step is just to calculate the aspect ratio to make sure that all are quite near to 1. So you just need to take the longer side, divide by the shorter side, and you can get the respective aspect ratio. So this particular table will actually sum up what are all the different duct sizes at the different section. Next, we will calculate the pressure losses along the longest duct. As you can see from the diagram, ABD is the longest duct and most probably it has the largest pressure loss. So we are going to focus on ABD, this longest duct only. So right from the start, when it comes out from the AHU, the first item that contribute to pressure loss will be the elbow over here. So pressure loss at the elbow before B will be the first duct fitting losses. Next, there's a junction over here, a cross junction. So junction loss at B will be the second one. The third component will be the VAV damper over here. So the third component will contribute to pressure loss will be the VAV damper, and finally the fourth one, which is the air diffuser, will also contribute to some amount of pressure loss. And the fifth one, of course, will be the pressure loss due to duct friction. Once you have identified out, you may want to write down a brief description such that it can remind you to calculate each and every one of them. First, we will calculate the pressure loss due to duct friction. So remember the general formula is friction loss multiplied by distance. So the friction loss in this example is 1 Pascal per meter, and the distance we have to refer back to the schematic. So over here you can see that the friction loss, we assume it to be 1 Pascal per meter. As for the distance, for ABD will be 20 meter plus 4 meter over here plus another 12 meter over here. So total is 36 meter. Take note that you shouldn't add in the side branches. That means the 8 meters side branches you shouldn't include in your pressure loss calculation because we are only focusing on the longest duct. So 1 Pascal per meter multiplied by 36 meter will give us 36 Pascal. So we have calculated the first one. As for the next two, we are going to use the general formula half K rho V square. So the K value is given in the question, and velocity, we will have to take note the correct velocity to use. The K value for elbow is 0.7 and the K value for junction is 1.3. So let's say you are able to get these two values from the manufacturer. Alright, and the velocity we are going to use is, let's look at the elbow first. Elbow is over here. It is sitting on the duct section AB. So duct section AB, as we have retrieved from the friction loss chart, it is 9 meter per second. Alright, so for the calculation of pressure loss at the elbow will be half K rho V square, and the V will be 9 meter per second. As for the junction, the velocity at the side branches is 7.8 meter per second. The downstream velocity is 6.3 meter per second, and the upstream velocity is 9 meter per second. So looking over here, the pressure loss that you need to calculate at junction B, you should always take the upstream velocity. So ignore the other two velocity, you will take the upstream velocity as the one for your calculation. And the working for the elbow and junction will look something like this. So half K rho V square. So for both junction and elbow, the velocity will be 9 meter per second. So you will get the other two pressure losses. Next, for VAV, how do we get the pressure loss? There are 3 VAV boxes over here, and the one that we are going to look at will be this particular one, because this is the only one that sits on the ABD section. So ignore the other two and focus on this. This VAV is sitting on section BD. So we are going to look at section BD velocity, and the velocity at BD is 7.8. So with this velocity, 7.8, let's refer back to this VAV chart. So this is 4 meter per second, 5 meter per second, 6 meter per second, 7 meter per second, and 8 meter per second. So 7.8 will just be in front of the 8 meter per second line, and you have to draw a vertical line upwards until it cuts 75% open. So the point where it will cut will be somewhere over here at this particular point. So draw a horizontal line to the left until it cuts the vertical axis, so it should be over this point. So this is 30 Pascal, this is 40, over here is around 32 Pascal. So the pressure loss at the VAV will be 32 Pascal. And finally, they also ask for the diffuser loss. Let's say diffuser loss, in this case, you are able to get from pre-calculation, and it's 22 Pascal. With these two pressure losses, 32 Pascal and 22 Pascal, you can sum up all the 5 different pressure losses, and the total pressure loss will be 187.2 Pascal. So a conclusion will be this particular AHU fan must be able to deliver 3600 liters per second of air, and it must give a pressure rise of 187.2 Pascal.